Moving on to the next part of our vectors, it's actually a extension of what I've actually gone through in the basic properties video. So if we recall in the basics properties, we talked about one of the properties, which is if we have the vector ka, well, it would just be ka, right? So let's say if we have k 1, 2, 3, then it will be 1 times k, 2 times k, 3 times k. So k, 2k, and 3k. So far pretty simple, right? But there's also another significance on this idea of a constant scalar multiple multiplied by a vector. And the idea is that if we actually think about vectors, it's just simply the change in coordinates. All right. So delta in coordinates. And it could be from anywhere, right? So let's say if you look at this example, we notice that A and B, A to B is a certain vector, right? Let's say we have it 1, 2, 4. And CD is parallel to AB. And if you recall from the ideas of our lines, if two lines are parallel, they will have the same gradient, aka they would change, the coordinates will change in a same way. Similarly in vectors, if two lines are parallel, the coordinates of the vector would change in a similar way as well. So in this case, if CD is parallel to AB, and AB is, well, the vector of AB is 1, 2, 4, then CD would also be changing at 1, 2, 4. But of course, CD might be longer or shorter than AB, so we can then apply a constant k to it, right? It's a scalar multiple of it. The idea is that AB is moving in the same direction as from C to D. It's just the matter of the magnitude or the length that you go from A to B versus going from C to D. All right, so the direction is the same. But, the magnitude may not. So the length or the magnitude may not be. So that's the whole idea here. And that's the reason why, if you like to prove parallel vectors, or for the H2 math syllabus or even the E math syllabus, parallel lines, then you just need to show that the two vectors are parallel. That's right, the two vectors are parallel because they share the same basic vector, or aka the factorized vector. So let's say if we have 2, 3, 4 versus let's say 6, 9, 12, then you notice 6, 9, 12 is 3 of 2, 3, 4, and therefore let's say we name the first vector A, second vector V, then we know that A is parallel to B. On the other hand, if we let's say have 1, 2, 3 and the other we have 2, 3, 4, then clearly, all right, C is not parallel to D, because we cannot express one as a scalar multiple of the other. All right, so to prove parallel vectors or lines, you just need to prove that one vector is a scalar multiple of the other. And this scalar multiple can be positive, can be negative. It doesn't matter. And it can even be between 0 and 1. All right, so this is the whole idea of parallel vectors when Ka is essentially parallel to the vector A, and that will do it. Now another property that is important is if we were to at least recall, or rather use that property of knowing that parallel lines, right? So let's say I have a line. Let's draw a proper straight line. Oh, whoa, this is a circle. Wow. Okay, something's not right. All right, great. So if we have a line, let's say we have this as line A and B again. So what's going to happen is that in some questions, they would tell you that, hey, now we introduce a point C that will occur in the somewhere along the line, all right, or rather point C and not point E. And they tell you that AC is to CB or BC is, let's say, 2:3. So let's say if we give the vector AB as, well, let's say, what's a good number? I don't know, let's use 1, 2, 3 again. All right. And well, essentially, we know that AC is definitely parallel to CB, right? Because they're moving in the same direction. And a more specific term is called they are collinear, but I'm not going to introduce that term now. So what happened is that since they're moving in the same direction and they're on the same line, aka they're collinear, and because they're split by the ratio of 2 and 3, we can easily know that if this whole thing is 1, 2, 3, whoa. If this whole thing is 1, 2, 3, then of course you just, and this is 2 units to 3 units, then you just simply, divide by 5 and then times 2 times 3. So simply, this is 0.4, and then this 0.8, and then 1.2. CB, so this is A to C, and then A to B, or rather C to B, is simply, so 1 divided by 5 times 3, so that will give me 0.6, and then for the ratios, 1.2, 1.8. All right, you notice that they're still parallel to 1, 2, 3. All right, if I factorize out 0.4, this will be 1, 2, 3. If I factorize out 0.6, it will also be 1, 2, 3. And you notice that, hey, 0.4 is to 0.6 is indeed 2 is to 3. All right, so this is how we can actually use the properties and actually solve questions involving ratios within a line. All right, let's say we have a point C that divides 2 points or divides a line into a specific ratio, then this would come in handy. Alternatively, another scenario is they give you a line and then they tell you that this is A, this is B, and then tell you something produced. All right, so AB produced, so which means you extend line. I'll go through that example in the following video after I talk about the ratio theorem. All right, so there we have it, the idea of scalar multiplication of a vector, of using it to prove parallel lines or parallel vectors, and also introducing the idea of ratio.